All right, welcome back. So today we're going to be talking about observation and measurement, which seems very, very simple, but actually can be very confusing in some ways. So I'm going to try to break it down as best I can. Again, after this video, if you have any questions, feel free to come talk to me. We can talk more one-on-one and everything like that, but we'll just get right into it. So there are a couple of types of observations, two main ones. One is what's called qualitative. So a qualitative observation is a descriptive observation. The main focus is trying to describe what you're seeing, what you're touching, feeling, anything that uses your senses. So, if I have for example, if I said copper 2 chloride has a bright blue appearance as a salt with smooth texture, that would be something that's described as a qualitative observation. The second one is what's called quantitative, which is probably the one that you're more familiar with. Quantitative is a numerical observation, something you can assign a number to. So it's something you can assign a number to with its units, which is very important. So always have a number and its units. So an example would be I obtained 33.5 grams of copper 2 chloride from the reaction. So it's a numerical value of weight or of mass, that I grabbed of copper 2 chloride. So that's very important to distinguish. So again, when you see numbers and units, it's going to be a quantitative observation. Qualitative is going to be more describing the visualization of the thing that you're looking at. So a big thing going into units is what's called SI units. So in the world of science, something you may be already familiar with, generic or general standard for quantitative observations is to use what's called the International System of Units, which is also called SI units. It's a universal thing that we use for science, so that way when we're building the parameters of our experiment, we know exactly what type of equipment to use, how we should set, how far things are, how long we should run the experiment, so on and so forth. So it is a revised version of the metric system. The International Committee for Science is actually in Europe, where the metric system was derived from. So that's why and how they came up with that. Which a lot of you guys know that the USA is really one of the only countries that use the English system. If you go anywhere else, it's always the metric system is everything you see. That's the reason why when you get into your car, you'll see, like, for miles per hour, you'll also see kilometers per hour, the km for kilometers. It was adopted by the scientific community in 1960, so it's actually not that old in regards to just the scientific world and the history of science in general. I mean, science has been going on for thousands of years, but it's just recently where scientists of the world, when technology started becoming more advanced, we started checking each other's work, we wanted to make sure we were all on the same page, so that's one of the reasons why they developed this system. It is based on multiples of 10 mathematically, and I'll get into how that really looks here in just a second. It uses base units for standard measurement. I'll talk about the base units here in a little bit as well. Base units can be preceded by prefixes, which you guys should know from English. It's a couple letters that are set before a particular word to indicate smaller or larger values based on for a condensed literature format. So when I say kilometer, meter is the base unit because it's the unit of length that we're using in the SI system. But kilo means 1,000. So when I say 46 kilometers, it means 46,000 meters. And we'll dive further into that, but that's kind of what it's built for. So when you're reading papers and reading textbooks and everything like that, that helps you understand what they're talking about. So again, kilogram means 1,000 grams, kilo meaning 1,000 as a prefix. So these are some of the base units that are used in chemistry. So how I've broken this table down is the dimension that we're trying to define is on the left-hand side. The base unit that we use is in the middle, and then the symbol for that base unit is on the right-hand side. So length, we use meter always, and meter is defined by a little m. Mass, not weight, mass is defined by gram, which is represented by a little g. Time, a lot of people think is in minutes, but it's actually, we define it in seconds. And that's represented by a little s. A couple of other ones that we'll get further into later in the year. The amount of a substance is what's called a mole. No, it's not the little thing that burrows in the ground, has little feelers, is the blind mole rat thing. It's an amount of a substance. It's based off what's called Avogadro's number, which we will dive further into later this year. And it's represented by the symbol MOL. Temperature is 9 degrees Celsius. It's 9 degrees Fahrenheit. It's in degrees Kelvin. The reason why is because Kelvin does not go below 0. It goes from 0 up. So Fahrenheit and Celsius can go into negative values. But for mathematics to work in regards to what we'll get into, like gas laws and everything, you need only positive values. So that's the reason why the Kelvin scale is determined. So when you hear the term absolute zero, it actually means 0 degrees Kelvin, because it's absolutely the lowest temperature can go. Now, volume is base unit of liters, which you guys are probably familiar with, like liter pop bottles and everything like that. But the weird thing is volume is not a particular dimension by itself. It's actually derived from a unit of length. So it's not specified as an SI unit, but in the world of science, we treat it as an SI unit. So that's a little confusing. It's a little thing we kind of get away with in the science world, but it's technically not an SI dimension. It's derived from length. So mass to volume relationships kind of help re-emphasize this a little bit. The conversion of a base unit to base unit is derived from things that occur in nature. So the way we came up with SI units and just units in general is that, scientists way back when started looking at things in nature and saw this consistent measurement that could be made. And so they started using these natural elements, these natural occurrences, to define units of length, volume, mass, everything like that. So that way, when we described our scientific data, it was something that we could further understand as a human race in general. So, for example, length, volume, and mass are all related to properties of water at certain conditions. So to kind of illustrate this a little bit, 1 gram is the mass of water at 4 degrees Celsius, or 277 degrees Kelvin. And it's because it's at where water is most dense. So since water is, 75% of the Earth is covered, 70% of the Earth is covered in water, and 70 to 80% of our bodies are made of water-based molecules and materials. It was very important to kind of base our scientific relationships off of this, and also the versatility of water that later we'll explore in the year as well. So another thing is that 1 milliliter of water is also equivalent to 1 centimeter cubed volume of water. So that's a centimeter by centimeter by centimeter. That makes a little cube. So 1 milliliter is equivalent to 1 centimeter cubed, and it's at these exact same conditions. So based off that, what we can do is we can create a relationship between mass, volume, and length, which mass is defined by gram, volume is defined by milliliter, and then centimeter describes length. And so you can create something like this. Now, this is very important. I do highly recommend writing this down somewhere, memorizing it, because you will be using it all the time. Like, no kidding. So write it down somewhere, like in your notebook or in your notes, somewhere you can quickly reference it. That way, if you forget, you're not scouring your notes for everything. But it is something I would highly recommend memorizing for this course. So SI units, prefixes, this is just for normal notation, and I'll kind of dive into what that means here in just a second. So this I have this big table here. So the way this works, you guys probably, again, have dealt with this maybe in middle school or in physics last year, but your base unit is where it's going to be right here in the middle, and the base unit just represents a unit of 1. That's it. Now, as prefix value, since the base unit is just the base unit, like 1 meter, there's no prefix in front of it, so it just means 1. So 1 meter is 1 meter. Now, going up to kilometer, if I put kilo in front of the base unit value doesn't change, but the overall value does change because I'm putting kilometer, which means 1,000 of these ones, which means 1,000 meters. Okay, same thing with mega. That's 1 million, so there's 1 million of these ones. So a megameter is 1 million meters. Now, if you go down, you can go down the exact opposite way using deci and centimeter. So centimeter is something you're really familiar with. Is the base value doesn't change, but centa means 1/100th of a meter. So that's why you can say 1/100th. There's the 10th place and the 100th place right here. Milli means 1/1000th of a meter. So For every meter, there's 1,000 millimeters, micro and nano. There are other prefixes, but we shouldn't be going any smaller or bigger than that. If you want to look into those, feel free to Google those. I'm sure you can find those or come talk to me because there's plenty of other ones as well. So going into scientific notation, you can also use the prefixes to help describe scientific notation in regards to the exponents. So it's the same, pretty much the same chart, but instead of the prefix values with just the whole numbers, now we're in scientific notation. So you can kind of notice a little bit of trends here. So when you go from base unit, it's just 1. 1 times 10 to the 0 if you really want to. So it's just 1. That's the same thing. But kilometer, there were 3 zeros in kilos. So that means there's 3 up on the exponent. And then mega goes up to 6. And then giga goes up to 9. So when it comes to bigger values, we only really count in threes when it comes to that, when it comes to prefixes. I mean, we do deal with numbers with it's like 10 to the 5th or 10 to the 4th or whatever, but we typically don't assign any prefixes to them. If anything, we convert them into an exponent that would represent a prefix on this chart. So if I was to say I had, I don't know, 10,000 meters, I would say 1 times 10 to the 4th. But what I could also say, I can say 10 times 10 to the 3rd, and I could say 10 kilometers. So it's the same thing. So that's one thing to be aware of. Now, when you get down to the negative values, you can see that deci starts at -1, then there's centi at -2, and then milli at -3, and then micro and nano. The reason why is that there's a lot of derivation, a lot of things that can be found in between these exponents, which is the reason why it doesn't jump up to 3 like these big ones. As you'll come to realize, chemistry deals with a lot of micro stuff, which means we have to be more precise and accurate, which means we need to use numbers and nomenclature or definitions that deal with more intervaled number sequences, which is the reason why we go -1, -2, -3, then -6, and -9. So quantitative observations. So when you're making quantitative observations, you always need to remember every number needs a unit. I'm going to say this right now, which I'm pretty sure I've probably said in class already. Unless for some reason that number does not need a unit in your calculations, if you don't have a unit on your number answer, it's wrong, or at least partially wrong. So you need to start getting in the habit of assigning units to numbers every single time. This is very important, not just in chemistry, but in any science field, is that if you don't have units when they're not supposed to be there, it leads to discrepancies. It can lead to people not believing your work. I mean, there's a lot of stuff that can go into it. So it's really for your own good. I know it might be annoying, but trust me, after you do it for a while, it'll become such a back of your hand kind of thing that you won't have to worry about it. As you'll come to find in chemistry, there are special cases, like I just said, in which some numbers do not have to have units. However, this is only about 1% of the time, which the 1% that we're probably going to talk about in the next video called error analysis. But there's a couple other things that may not have units too, and I will help describe those as we come across them and demonstrate why they don't have units. But other than that, each number should always have a unit unless proven otherwise. So if you ever have a question about it, does this thing require a unit or not, come talk to me, and we can kind of break it down one by one and see what's going on there. But besides that, that's all for this video. If you have any other questions or anything, feel free to come talk to me. Feel free to refresh your memory on these other videos in this unit as well. And I hope to see you in class and hope to see you next time. Bye.